as needed. Cool. Okay, so today we're going to be having a look at we're going to continue on with our polynomials exploration, namely into how we sketch higher degree polynomials like quartics and above, and then also moving into the applications of polynomials, where do we actually see these in, quote, real world scenarios. For the moment, my phone camera has decided to crash. We will bring that in as is necessary when it becomes relevant. But okay, cool. Let's see. So the first kind of topic that gets brought up in these higher order or higher degree polynomials is this idea of the odd or even polynomial. Easiest way to think about it, the power of the, when it's in its completed square form or turning point form, the inflection point form, whichever of those basic versions you want to call it, that power of n fundamentally is going to determine whether it's an odd or an even polynomial. It's the most basic way of thinking about that. Any odd polynomials in that form are going to essentially become steeper and steeper cubic-like shapes. So you can see the green line is the x cubed, and then everything else is increasing in power, and what you end up seeing is it gets steeper and steeper on the as it gets further away from the origin. It is also referred to as an odd function, which has this specific property. You can prove any function is odd as long as this is true. Now, mathematically speaking, that's pretty easy to prove, right? You just have your function, first figure out what f of negative x is, and then simplify that result. Just keeping in mind that any odd powers will always preserve the negative that's in there. And then for negative f of x, exactly the same thing. You're just going to put a negative out the front of the whole thing and distribute through. So as far as proving that they're odd, you just want to compare the two. Are these two things the same? In this case, they are. Therefore, this is considered an odd function. What does it actually mean? Well, that property there essentially means that if you imagine this point 1, 1 that exists on the graph, if you were to flip that down and, well, vertically and then horizontally, or the other way around, you'll end up at the negative version of that point. So this is 1, 1. If you were to flip this vertically and horizontally, you should get to negative 1, negative 1, which is what this is essentially telling you. So it doesn't have to be a cubic. It can be any other type of shape, so long as it has kind of like this diagonal symmetry going on to it. There's a bit of like a sort of reflection in the line y equals x, but not quite. You can see how it's kind of like inflecting in the middle and kind of mirrored, but a little bit different. That's the idea of an odd function anyway. For even, all you have to do is be symmetrical about the y-axis, either side of it. That's the gist of it, really. So as long as you have that, you're fine. The mathematical way to prove a polynomial, or any function for that matter, is even, is such that f of x is the same as f of negative x. So again, the proof of that is just a matter of, well, we already have f of x, so really all you're going to find is what f of negative x is, keeping in mind, of course, that when you solve that, any of the even powers will cancel their negative terms down to being positive. So any questions so far as that? It's a very minor thing that gets touched on. Oops. Yeah, it's not something that really shows up in your SACs or exams, usually speaking. Cool, okay. The meat of it is going to be in how we handle the factorized polynomials. So last week we had a look at the cubic factorized versions. Now we're going to have a look at what happens when the powers get bigger. Basically, a lot of what you've already learned is still going to be relevant here. There's only going to be two main things to consider. Instead of just thinking about repeated linear terms as being the turning points on the x-axis, we now have any even power version of that term will also be a turning point. So any 2, 4, 6, 8, any of those even numbers will all be considered turning points on the x-axis when simplified. And the new one, which is only kind of new, is that if you have an odd power linear term, what you now have is an inflection point on the x-axis. Now, I'm excluding the power of 1 there because that would bring it back to being linear, in which case it would be a cut, but any odd power greater than 1, you're going to see an inflection point on the x-axis. And so to take it to the extreme, we're not actually looking at a quartic here. This is a power of 10 function. Mainly there just to demonstrate the concept. Doesn't matter what numbers are thrown at you. The only things you're really looking for are whether it's odd or even. So, as normal, when we're solving our polynomial graphs, find the x and y intercepts via null factor law and just subbing in x equals 0. That gets us all of our solutions. This was an odd power term, so its solution is therefore going to be an inflection point. This was an even one, it's going to be a turning point. As for why is it a power of 10 function, you're simply counting the number of x's that are in the function. So it's 4x's here, 5x's here, 1x there. It's going to make a total of 10. As far as getting the final sort of shape right, you're looking for whether this is even or odd. So if we had a look from before, all the even type polynomials were basically just quadratics, right? They started and ended at the top, left or right. All of the odd ones were basically cubics. They started bottom left, ended at the top right. So when we have our power of 10, net power of 10 for this, that means that our shape should overall be quadratic-like, in the sense that being a positive quadratic, it should start and end at the top of your graph. So that's what we do. Then, in order, we're just going to write out our x-intercepts and make them either cuts, inflection points, or turning points. This was a cut, so the x equals 1 should be a cut, which sure enough it is. It cuts all the way through. The x plus 1 gave us x equals negative 1. That was a power of 5 term that it came from, and so because that's an odd, that's going to be an inflection point, which again, sure enough, you can see it wobbles there. And, well, the other one was a turning point, right, because we had a even power in there. So it's going to turn now. So you would start at your top, do your inflection, cut through the y-intercept, and then, just continue to follow your nose. As far as the magnitude of like how big you draw these curves, it's totally up to you. You set your own scale for these sorts of things. So whatever makes sense for you is what works. You won't be getting a graph like this. This is just to demonstrate the point of mainly when you get into like your tech actives and things get more complicated, it's good to have these fundamentals of knowing, hey, what do each of the terms in my graph actually look like? Because in your tech active, yeah, you can graph it, but sometimes what they'll end up doing is they'll chuck other variables in there such that it makes it kind of difficult to graph. Because as soon as you have more than just a y and an x, as soon as you have like a k in there, for instance, you now have to put a slider on your cas, and the behavior of how that graph is going to look will change depending on what you set for k. So knowing high level conceptually what these terms are doing bypasses you having to plug and play, guess and check a lot to get there. You'll just sort of know conceptually what they'll end up, what the overall behavior of the graph will be. Yeah, and just like we looked at before, actually finding these turning points is exclusively going to be done via the calculator. You're never going to do this. Even tech-free with calculus would still take quite a while, and so for that reason, it's usually reserved only for tech active. That's pretty much it. It's only like a little bolt-on to what we were looking at before with how we sketch polynomials. Not something that comes up too often, but having good fundamentals of polynomials in general is really strong to have because of the weirdness that comes up in your tech active stuff. That's it for this part. Anything in there that I should clarify further? Could you do an example? Didn't fully get how everything works. Yeah, sure. So let's see, what kind of example? Yeah, this might work. I guess I could just make my own up and we can take it from there actually, because these are going to be a bit different to what I was describing there. Like for instance, you can see how it's telling you to use the cas immediately. So it's not super helpful to look at these because you would just plot it on the cas without really thinking about it. So I'll just make one up and we'll take it from there. The camera is back in, by the way, if you want to hop on over to that. And we'll do one live. So let's see, we should have a linear term. So we should have, I don't know, let's go x plus 1. We should have an odd term. Let's go x minus 2, make it 3. And we should have an even term. Let's go x plus 4. And yeah, why not? Just make it 4. So the key things that we should be looking for here are whether we have linear terms, even terms, or odd terms in the thing. That will determine the solution to that term as either being a cut, a turning point, or an inflection point. The odds are inflection points, the evens are turning points, and any linear, just like any other function, is always going to be a cut here. So when you're finding those x-intercepts, first things first, get your solutions. So you've got your x plus 1 equals 0, x equals minus 1. That's going to be a cut because it came from a linear. Are we tracking so far? Slow me down if I'm going too fast. Next up, the x minus 2 equals 0. That's going to get you the x equals 2. Because that came from an odd power term, that's going to be an inflection point. Sorry, could I repeat? Yeah. So to repeat what I had there, linear, always cut, no matter what. So all we're really doing right now is doing our null factor law to get our x-intercepts. And then based on the solutions of that, whether it came from a linear, an odd, or an even, will determine what type of x-intercept it is, whether it's a cut, turning point, or inflection point. So linear just meant cut. The cube, because that's odd, means it's an inflection point. And when we get this solution, because it's even, will be a turning point. X plus 4 equals 0, x equals minus 4. Those are the key things there. As for your y-intercept, that's just going to be x equals 0. So y equals 1 times minus 2 cubed times 4 to the power of 4. That's just some big number. Question, so it's odd if the power itself is odd, and yeah, absolutely. You're simply looking at the power of the term itself to determine whether it's going to be an inflection or a turning point. And if it's no power, it's always a cut. This will just be some some net negative number. Doesn't really matter what it is. And then yeah, as far as graphing it, first thing you'd probably want to do is put all your intercepts down. So we have a -1 solution, we have a 2 solution, and we have a -4. We have some negative y-intercept down here, whatever that was. And the only thing left to do is to figure out the overall shape. So maybe I'll pass that one back to someone. Based on what I was describing there, when it came to figuring out like how we start, does anyone remember what I said about how to start it out? Got something to do with the overall power of the function. Adding up the powers, yeah, adding up the powers is correct. That's going to tell us something specifically. So adding up the powers, we're going to get power 8 there. So this is an x to the power of 8 type graph. There's only ever two possibilities for these types of graphs. They are either quadratic-like or they are cubic-like. Does anyone remember or want to take a guess at which one the x to the power of 8 type graph would be?
Cubic-like.
Cubic-like? What makes you say that?
Because there's 3 x-intercepts.
3 x-intercepts. Fair enough. So 3 x-intercepts, I get what you mean, because if it does something like this, that's kind of the only way that can work. So that's a good observation there. The only challenge with that is they're not all cuts necessarily. we have one that's got an inflection in there, and we got one that's a turning point in there. So even something as simple as it doing this instead, that's not the graph, would also have that same number of intercepts, but not be a cubic. So I understand that, yeah, you got your 3 cuts, and that makes a decent amount of sense for a cubic. The way to determine whether it's parabola-like or cubic-like is based on whether it's even or odd. That's the main thing by far. So even, you got your x squared for parabola. Any even is going to be parabola-like shape. Any odd would be the cubic shapes. That's what I was covering at the start of the class there, based on whether it was an odd or even function. So because it's power of 8, we know it's going to be a parabola type shape, and it's positive. Right? If we look at the sign analysis here, you've got all positive x's, it's going to be a net positive. So we know we're going to start and end something like that. Everything else is going to be based on what we see here. So the x equals -4 solution, we know has to be a turn. So we turn. The x equals -1 solution came from here, so it has to be a cut. So we cut through there. And the x equals 2 solution has to be an inflection point. So we'll go through our y-intercept and then inflect there. A bit of a poor inflection, but that's the gist of it. And so yeah, even though we have a number of intercepts there, those intercepts could count for 2 or even 3 terms because of how they were squared, cubed, power of 4, whatever they were from where they came. And that's the gist of how you're going to get basically any polynomial that comes up. Could you re-explain how it's a cut, inflection point, or turning point? Yeah, so I'll bring it back to the screen share at this point then. So the summary is as follows. So your polynomial is going to be made up of either linear terms or linear with a power. Like that's the bare bones basics of what you get for polynomials when they're factorized. So always going to have some linear term. It may or may not have a power. If the power is even, it's a turning point. If it's odd, it's an inflection point. That's all it was. So it's all we're doing is expanding on what we looked at last week, which was if we had those even, or power of 2, it was turning point. Now we're just extending that further to say, actually, all even powers are turning points, and all odd powers are inflection points. Anyone want me to clarify anything further on that? And what about the cut? The cut is just basic linear. So any basic linear term is the x intercept, the cut. So that. If there's no power on it, or power of 1 implied, that's always going to be a cut. Any other questions? Cool. Okay. If any come up, I'm happy to go back. But for now, applications. So this is the stuff that'll show up a lot in your Saxon exams, especially. How we work with actually applying this polynomial stuff to more of the real world scenario type things. One of the minor applications that come up more so in like your show that type questions or otherwise are going to be your families of functions style questions. Point being, you'll have either a fully generic polynomial or function, or it might have some terms already in it, and your goal is to figure out what the other terms are. We're going to look at the absolute worst case scenarios because that'll show you how you can handle the worst case scenario. Anything better than that will just be less steps involved or easier in some way. So if you know how to do all of it, you'll definitely know how to do some of it. A lot of the time, you'll be given a type of graph, or sometimes you'll just be given the key features and told what they are, whether they're inflection point, whether they're just a regular point, so on and so forth. One of the challenges with polynomials specifically is that there's so many ways of writing them up. So you could have the polynomial form just fully expanded. You could have a factorized form, or you could have the inflection point or turning point form of your polynomial, depending on what that power was. The form that you use will depend on the information you have. So for instance, if you're given the inflection point as part of your key information, probably a good idea to start with the inflection point form of your polynomial. So you start with a fully generic inflection point form, and because you know this point is at 3, -1, that automatically gives you your B and C terms, or usually those are written as the H and K. From there, there's only one variable left. This will always be the case for these kinds of questions. And sure enough, there's one point left to use. So you sub in your point, simplify, and you get your A value. If the question is asking to solve for A, B, and C, you don't give the curve. You give A equals 2, B equals -3, C equals -1. If it is asking for the function or the rule, then you give the thing highlighted in green instead. So a bit of a nuance there, because you will be Dr. Mark, as punishing as that sounds. You will absolutely be Dr. Mark if you give your answer in the wrong form. Next kind of thing is if you're given a whole bunch of x-axis intercepts. We looked at this kind of the same in quadratics as well, where if you had a bunch of x-axis intercepts, it's best to start using the factorized version of the polynomial, because the solutions to those factors are the x-intercepts. So, if you have your cubic and it goes through those points, you immediately know you have x minus 1, x minus 2, and x minus 3, simply because those are the factors that would get you 1, 2, and 3 as the x-intercepts. Again, a is left over. Don't forget to put that a in there, because a lot of the time they won't say, hey, start with this. They'll just say, here's the picture, work it out yourself. And a lot of the times, a key thing to forget is to put that a at the front. Because depending on how stretched this graph is, you won't really be able to tell, because the axis will always look a little bit different. And so yeah, you just plug in your remaining point, as we did before, solve for the remaining variable. Again, that whole spiel on whether you give the function or the actual letters themselves will depend on what the questions ask you to do. In this case, it says find the equation, so we are giving the equation. This is just a slight nuance on it. Yes, we're still given both x-intercepts here, but one of them is a turning point, so we're just going to make sure we put in a squared term in there. Fun point on that, I did just go ahead and do a whole spiel on how technically any even power works there. Make it easy for yourself. Don't pick a stupidly big even term, even though it would technically work. Pick the easy one. Just pick a squared term, because that'll be the basic version of getting that there. But yeah, that's the -2, so that's going to be the x plus 2 that belongs there. This is a cut, so it's going to be just a basic linear on its own. And yeah, again, the a is going to be there. Sure enough, we have another point that we can sub in. Lastly is going to be CAS related. You're never going to be doing this tech-free. We went through a system of how to do that on the CAS. Let's revisit that again. This will work whether you're using the TI-Nspire or the Casio. The only thing that's going to be slightly different is where it's located on your CAS. So if you don't know where this is located on your CAS specifically, let me know and I'll bring up the other one. I do have the Casio as well. Okay, so how do we do this simultaneous? For TI-Nspire specifically, you're going to menu 3, 7, 1. You're doing solve system of equations. That's where you go. What you'll want in this case, because you have 4 points, is you want 4 equations, and whatever they're called in the question is what you'll label them. And that sets up the window that you'll have. Now, that was just me showing you where to get it. Before you do that though, easiest to start by defining what the generic polynomial is. So you would look at your screen and you'd be like, oh, I guess your paper, and you would be like, okay, this is a cubic, right? It's got your 2 turning points. It looks like some sort of factorized cubic. So define a generic cubic in your CAS. Ax cubed plus bx squared plus cx plus d. Exactly the same on the Casio. You'd also want to define it as well. Yeah, define it properly. How about that? Define function equals that. And the syntax is the same on the Casio as well. Now we can go ahead and do what we did before. For those wondering how I got that, you can just Control-C, Control-V, or Control-X. All of that works on the Cas. How does it help by defining the function behind? You'll see right away. So we've got a whole bunch of points on our graph. We need to translate those into equations. So one of the points we have is -2, 7. Here's what that looks like when you define it beforehand. You just write h of -2 equals 7, versus having to do 7 equals a times -2 cubed plus b times -2 squared plus so on and so forth. You'd have to write out that whole thing 4 times in total. So define it once and then never again. H of -1 is equal to 8 is the other point. One of them's kind of a bit hidden, which is we had a y-intercept. So just remember that's x equals 0. And then h of 1 equals 4. Hit enter, you get all your coefficients. Just keep in mind where those actually came from, right? So if you're given if your answer is to try and give the coefficients, then by all means just give that. If you're trying to give the function, make sure you put them into the actual polynomial itself. As for the Casio, if you look back at the screen share, I do have where that's located. So if you pull up your Casio, you'll have a Math 1 window. It'll be this button specifically highlighted in red. All you'll do is you'll hit that a couple of times until you get 4 equations, and exactly the same as before. Does anyone need me to work through that on the Casio specifically? Or is the concept clear enough there? Cool. Okay. Now, another very common question that will show up will be to find either the maximum or the minimum of a certain quantity. Usually you're doing maximums, although it doesn't really matter whether it's a max or a min. The procedure is identical. All you'll be doing is interpreting it a little bit differently. So, how do we do it? This right here is a generic procedure for doing any maximum or minimum problem. You could work with any function on this, but the vast majority of the time it's going to be some sort of polynomial, usually a cubic or a quadratic. Quadratics, you'll typically be doing area stuff. Cubics, you'll typically be doing volume stuff. So here's one of our examples. We've got a square sheet of cardboard, has a certain set of dimensions, and we're folding it up into a box. In this case, we're told to find the maximum volume of the box. We're told to find volume, which means we need to start by finding our volume equation. It is a box, so length by width by height is the generic way of finding the volume of the box. In this case, we weren't given a picture in our actual problem statement, so it's a pretty good idea to try and draw out what's actually written there. A lot easier to look at a picture of a thing versus just sort of looking at these dimensions, because once you draw it out, it becomes a bit more obvious that you shouldn't actually be using 20 and 10 as your dimensions for the box, because there's these cutouts involved in there. So you can imagine if you were to fold this one up and actually make a box, what you would actually have is these cutouts of x and x. So essentially, instead of the width being 10, you now have 10 minus 2x. You're cutting out those extra bits out of it. Same thing with the length there. It was 20, but you're cutting out 2x's worth. That gets you length, that gets you width. Height, for those who haven't done this experiment before, please do. Just get a piece of paper, cut it out and make a box. Because what you'll need to understand is that the cutouts that you're using end up being the height of the box itself. So if you cut this out and you imagine folding this bit inwards, the height of how it would stand up would be x. So your height is just x. This is a lot easier to work with, because instead of having 3 or 4 variables, you've now only got 2, the v and the x. That is something you can actually sketch. Now, if you're tech-free or tech-active, whether you continue to factorize it further is up to you, because the question isn't asking you to get the rule of the volume. It's asking you to maximize it. It doesn't actually care what you have as that, as long as it's going to get you to the right answer. So whether you take out a common factor of 2 from both of these or not is purely up to you. As long as you're in a spot where you can sketch that and get an idea, that's all that matters. So this is going to give you the x equals 5, that's going to get you the x equals 10, and that's going to get you the x equals 0. It is a net positive because you've got negative, negative makes positive, and then positive once more. So it's going to start bottom left and top right. This is a very common shape. It'll pretty much always end up being this initial hump that you're looking for there. The reason why the rest of the graph isn't valid is because we're working with an application, right? What x actually is a physical quantity. It's the cut out of the cardboard or paper or whatever we have. So you can't cut out negative from it, so all this negative x is irrelevant. And you can't cut out too much either. You're capped out at a maximum of 5 that you could cut out, because you cut out 5 from this side, 5 from that side. You can't just say cut out 10 in total. Remember, x is one side of the portion that you're cutting out. And sure enough, that's going to cut out there. The other way to think about it would be you can't have volume go negative. Remember that volume is on the y-axis here. So it usually, most certainly, will end up being just this little hump here. One point of order. This is a cubic. Don't assume the turning point is going to be dead center. It's not. It tends to be a little bit lopsided towards the origin rather than towards the right-hand side. So don't just assume it's the dead center and then sub in a point. You do have to go through these procedures to now figure out what actually is that turning point. Because if you're trying to find a maximum, well, there it is. That's the highest point on the graph. This is usually CAS related until you learn calculus. So we're just going to use either our graphing tools if we have 2 decimal places to work with, or any more number of decimal places, because your graphing tool, those solutions always come in a decimal, no matter what. As long as there is a decimal answer for it. If you need a exact answer, then you're going to do a CAS solve instead. That'll be after doing. It wouldn't even be a CAS solve, would it? It'd be an Fmax. Let's explore that a bit. So we'll pull up the TI Inspire, and we want to do our exact solution to this. You'll be doing Fmax, which is in the calculus menu for TI Inspire. And for Casio, do I have it written down? Yeah, I do. It's in a very similar spot for the Casio. Anyway, function maximum will return the x value that corresponds to the maximum of the graph. Casio works slightly different. It won't just give you the x value, it'll also give you the y value as well. So this is one of the only times where Casio actually does slightly better than the TI Inspire. But anyway, we got our 4x, 10 minus x, and 5 minus x. This is me just copying down the function. Comma x is the syntax. This is the same syntax for both the TI Inspire and the Casio. One thing you want to do is make sure you're defining a domain. So we talked earlier about how only that initial hump is going to be valid. So we're going to do exactly that. 0 to x to 5. That's where that cuts out. That is our exact form solution. If you did it on the graphing tool, you would have got that. That is not valid in if you're trying to give an exact answer. You want to give the top one instead. From there, we're just going to sub that into our function, which is why I should have defined it again. So let's just do that now. Define. That shouldn't be in there. Should be over here. Then grab a copy. And again, you get another exact answer. The Casio would give you both of these things. It would give you the exact x and the exact y. The exact y is what you want, because that is the maximum of the graph. And that's it. So that's all you ever do. If we go back to the screen share, first things first, figure out what's the generic version of the equation that gives you the thing you want. If it's volume, figure out the volume equation. If it's area, figure out the area equation. Get it in terms of one variable. And that's going to be using your picture and using the dimensions given to you to try and remove the length, the width, the height, and get it purely in terms of x. From there, you would draw a quick graph. Whether you do it by hand or by CAS will depend on whether you can do it by hand or by CAS in your test requirements. From there, you'll be able to see whether it's a maximum or a minimum quite quickly. Use your Fmax or Fmin for that matter, depending on if you get max or min. And yeah, I do have another thing here about how you can solve it by setting derivative equal to 0. That'll be what you end up doing later on because it's a bit faster. But for now, since we haven't done calculus, we'll leave that there. That's all the concepts there. So as far as applications, that's pretty much it. You got either families of functions, in which case you are trying to solve the equation of a thing, or you're trying to find the maximum or minimum of a certain quantity. And all of the work in those problems is going to be right here in step 1, getting the actual equation for it. So we saw how we had to go through and draw like a little picture to get a good idea. We had to then create our equation from that, simplify our equation, draw it up, and then we can work on the exact procedure that we just had a look at. This actually makes a lot more sense now because I've gotten, yes, you get a lot of these questions. Like if we look at even just this unit 1 and 2 thing here, right? Here's a volume thing. They're cutting it out, they're folding it into a box. Fun. Here's another box. Here's another box. Surface area. A little bit different, surface area, sure, but still fundamentally you just get the equation and then go through steps 2 to 4. Triangular prism, sums of lengths, any sort of quantity that's going on. A cone, you need to know the cone equation stuff. Good point is that a lot of these equations for the generic shape stuff is on your formula sheet. In fact, it's worth maybe just bringing that up now. We'll take a quick pause and I'll bring up the formula sheet that you'll get in your actual exam. So you can see ahead of time what are the things you actually get to have and what are the things you don't. This will be consistent for both your tech free and your tech active. Okay, so if you have a look at what we got going on in the screen share here, this is what I was referring to with the stuff that you get. So you get some cylinder stuff, trapezium, volumes for pyramid, sphere, cylinder, cone. You get a bunch of them. You don't get everything, right? They're not going to give you like the box, for instance, but if you guys are going to have trouble remembering the length by width by height, then we have more problems than just that. Once you get into calculus, you'll have all the basic derivatives and integrations and a few of the special ways of doing it. A lot of this stuff's later on. Probability, you might be used to some of these, maybe not this, but some of this stuff is generic probability. And yeah, this will be the thing that you end up with. So as far as what you'll care about for now, it's pretty much just this stuff. That's the only part of the formula sheet that matters right now. Yeah, that'll be it. Cool, okay. Is there anything about anything that I should clarify further? Or should we dive into some, probably applications would be the thing that matters the most here, getting good at those. What shall we do? So they basically give us all the key rules for calc. Yeah, that's it. So you got everything here is, you won't need anything other than this. And if/when you do, it'll be tech active. So your CAS will just do the diff or the integration for you. Cool, okay. Let's see if we can now start applying these applications. So what I'll do is I'll drop, I've messed up where my stuff was when I pulled up the formula sheet. Give me 1 second. Okay. So in the chat will be the homework doc that covers all the spots where you can practice these things. And what I'll also do is I'll drop the applications. Yeah, I'll drop the applications doc in here. That'll get you to follow the procedure there. I'll also have it up on the... Actually, no, I shouldn't have it up on there because you need a lot of the background information available. So try to grab a copy of the applications of polynomials. Either write down to the summary if you just want to see the key steps there, or well, you have a full work solution in there as well. We're going to go through a very, very similar example, so I'm hoping you guys will be able to follow along there and contribute. Let's see how that goes. Cool. Okay, so just going to go through question 1, essentially. You can imagine we've got a very similar thing going on. It is a square that has some edges cut out and folded up into a box. 1a says, find the length of each edge in terms of x. So in terms of like in an actual SAC or exam, they'll pretty much just go right down to D, which is just find the final answer for it, and you have to make all the steps up yourself. Ideally, you follow a procedure, but yeah. In this one, they're just leading you into it, right? They're essentially spelling out what you should do at each stage. And the first stage that they're giving to you is to figure out the length of each edge in terms of x. So I'll let you get settled for a bit, and then someone let me know how we're going to start this one out.
The edge lengths are 20 minus 2x.
Yeah, they're all going to be 20 minus 2x. That's absolutely correct. What made you come to that conclusion?
Because there's a cutout. Like if you specifically just look at one edge, you can see that there's 2 sections of x's being cut out from the 20.
Yeah, absolutely there is. You can see there's a cutout, and whether you're looking at the length or the width, it's a square. They're both the same thing now. So
yeah.
Our length is the same as our width, and both of those are 20 minus 2x. Nice. 1a done. Easy. Part B, so this will take us to the end of step 1 in the overall procedure. Find the volume of the box purely in terms of x. What might we do?
Since you're cutting out x from the corners, you know that x is going to be the height. So you do the 20 minus 2x squared times x.
That's exactly right. Yeah. Why'd you square the 20 minus 2x?
Because you need to find the area of the kind of the lower square and then multiply it by the height.
Yeah, that's right. So for the volume of the box, volume of any shape, by the way, which is what you're pointing out there, which is a fun little thing to think about. Any volume is just looking at the 2D shape, getting its area, and then multiplying by whatever its height is. That's a fun little thing to know depending on what type of shape you have, because you might have some weird shit going on like this, but you're told A equals 8 or something like that. And if you know your height is 4, well, you now have 4 times 8.
Dawn.
Even though this shape is a bit weird. So yeah, really good observation there. But yeah, since we have a box, length, width, height, there was 2 lengths, which is why we can just do a factor of 2 there. Yeah, okay, so that's our volume equation, and that's, well, we have to, it does ask us to find the equation specifically, so we probably want to factorize this a bit further. How do we further simplify it?
Would you have to expand it out first, or is there a better way?
I mean, it depends on your observation skills. I would go through and, like, even with all the quote skill that I have, I would still go ahead and expand it out a little bit. Oh, whoops. Just to make it a bit easier to see where the factors are coming from. Because you might be tempted to take a 2 out of this and then just call it a day. Whereas in reality, because there's 2 lots of this term here, taking out a 2 would only bring it out of one of these terms. You need to take out another 2 to make it further simplified. So in reality, you end up with v equals 4x bracket 10 minus x all squared. And that would be as simple as you could make that. So yeah, a little half step there of expanding things out to make it clearer for yourself is highly recommended, but not technically required if you are savvy to watch for this sort of stuff. Otherwise, yeah, that's going to get us the most simplified version of part B, finding the volume of our box in terms of x. Nice. The rest of these questions are honestly a little bit easier than what you get. They're just saying find the volume of the box when x is a certain thing, or find the value of x when the volume is a certain thing. Does anyone want to... Let's do them one at a time. What do you do when it's part C, for instance?
You would just sub in the value for
Yeah,
x.
exactly right. You're told x equals 5, so you're literally just going to do 4 times 5, bracket 10 minus 5 all squared, and that's just going to be some big number. Whoop-de-doo. Summing in a value. Part D, very similar. What's the nuance there?
You'd have to do 500 and then set it equal to the kind of formula that we've made for the volume.
That's it, yeah. So because volume is 500, V gets 500. And that's pretty much it. Now, yeah, solving this is a lot harder because you're not just subbing in a number and simplifying. Now you've got to do... Yeah, this would be like if you look at the book, it says it's all CAS. So you wouldn't be doing this by hand, because if you had to do this by hand, you would have to... Let's think about it. You'd have to expand everything out, bring this 500 in, do a factor theorem to try and get it into a proper factorized form, because for null factor law, this needs to say 0, not 500. So you have to go through a procedure of trying to get this into a factor set. Factor theorem, polynomial division, maybe another factorization for the quadratic afterwards. It'd be a whole procedure, which you don't have to think about because it's CAS. So you literally just CAS solve this. You just go solve bracket x, done. Yeah, so that's on the easier side of questions. It doesn't ask it, but I will now. I'm going to ask you guys to figure out what the maximum possible volume would be. So none of this is going to be relevant for that, so let's just clear up the workspace a bit. This will be the last bit that's valid, or relevant rather. We have our volume equation. You can use your CAS as well. We're going to use CAS methods to solve it. How are we going to figure out the maximum possible volume of this shape? Feel free to use the procedure that's written in my notes.
I think it's you kind of have to figure out the equation for that gives us the, I think it's the area or either the volume, and then just to graph that.
Yeah, that's right. So step 1 is get your equation that describes the thing you want. So if we want to find maximum volume, we need a volume equation, which luckily we have in this case. We did all those steps for that. And yeah, the next step absolutely was graph it, just like you said. We don't need a CAS to graph this, actually. Can anyone tell me what we would do to do this tech-free? This one would actually use last week's stuff. It only caps out at cubic. This will be a nice revision for the cubic stuff we did before. To sketch any graph, we need to know our x and y intercepts. How would we go about doing that here?
Wait, have we figured out the equation for the
Yeah, that's right.
volume yet?
It's the one up here, right?
Oh, okay.
Yeah. 4x and a squared linear term, what kind of observations can we start making?
We're just finding the intercepts first. So
Yep, finding intercepts, great start. How do you find intercepts for any function?
just you start by setting x equal to 0.
Yep, x equals 0. So that'll tell us what for the y-intercept?
So the first part you'd get 4 times 0, which is just 0, and then multiplied by 10 squared, so you get 100 times 0, which is just still 0.
Yeah, that's it, 0.
So
Nice.
yeah, both intercepts are at the origin.
That's it. Yeah, so we're going to have an origin specifically. That's good. There's one more though for our x-intercepts.
Oh, sorry, 10. Yeah, I didn't catch that.
Yeah, 10. So
Because, yeah.
that's right. Y equals 0. The y-intercept rather comes from setting x equals 0. X-intercept is y equals 0. So null factor law. 1 at 10. Cool. So those are intercepts, yes. But we can also tell what type of intercept they are, whether they are a cut, a turning point, or an inflection point. What do we know about? Let's start with the origin one. Is that a cut? Is that a, what is it?
Not sure.
Not sure. Okay.
Is it a cut because it's linear?
Cut because it's linear, correct, yeah. So even though it doesn't have a set of brackets around it, because it's basic linear, we call that a cut. Yeah. Good catch. So yeah, depending on if we come from the bottom, it'll cut like this. If we come from the top, it'll cut like this, which we'll discuss in a bit. And this one over here, what do we know about this to figure out whether it's a cut, turning point, or inflection point?
It's even, so I think it would be turning point.
That's right, yeah, any even. So to get your head around the even and odd stuff, I always refer back to the quadratic and the cubic. Right, quadratic has power of 2, that's an even number, and so quadratic is turning point. Cubic, that's always your inflection point. Well, mostly an inflection point. You can have the factorized cubic, but point being, yeah, your odds then become inflections. So yeah, we're either going to turn like this or we're going to turn like this, depending on something else. So we know we got a turning here, we got a cut here. How do we know where to start? So usually we've got to make a decision to either start up here or from down here. Oh my god, I can't. Okay, no, I can. I thought I ran out of space on my notes. I did. Okay, let's be conservative then. How do I know where to start?
I think you have to figure out whether the x's multiply out positively or negatively.
That's exactly what you have to do, yeah. So what do they multiply out to be?
Negative, because you've got the 4, you've got the x there.
Mhm.
Actually, no. Would it be positive because the negative x gets squared, which makes it positive again?
That's it.
And then with the positive x with the 4.
That's better, yeah. So the square can be a bit deceptive, so that's probably another reason why you might consider expanding things out just for your own sake. But yeah, negative makes positive, and then one more positive, as you said. So we know it's net positive. What does that actually tell us about where we start?
I can't remember if net positive start from the top left or bottom left.
Okay. To explore that, we are doing a cubic, so we'll look at the base version of the cubic. Do you know what this graph starts out as?
It starts from the bottom left.
Yep. That's it. Do you know why, or do you just sort of have that memorized?
Yeah, it's kind of memorized just from seeing the graphs.
Yeah, so this will be a nice thing for everyone. Like if you freeze for whatever reason in a lesson or in a SAC or exam, just start subbing in some numbers. So I'm trying to teach these higher level ideas of trying to compare it to simpler things. Like, x cubed is a pretty simple graph. There's not much going on with it. Versus this, there's a whole lot going on. So when I'm discussing these things of like, do we start top left or bottom right, or bottom left, because it's a net cubic, you can always compare back to this and decide, okay, cool. Positive cubic does this, negative cubic would do that. We have positive, so we're going to do the former, which would have us starting bottom, cut, and turn for all those reasons that we discussed earlier. Now, if this also gets you frozen as well, which is it's related to the cubic, but you don't remember how the x cubed works, because it's such a simple function here, you can just sub in values. Like, it's going to be one of these two, 50-50 shot. This is negative x, this is positive x. See what happens. What is f of negative 1? Well, negative 1 cubed is negative 1, so I should have a dot down here. Okay, if that's still not enough, maybe test another dot out. What's f of negative 2? Well, it's going to be negative 8. I've got another dot down here. Cool. It's going to have that sort of shape in there. So yes, that's slow, but it's better that you're not getting it at all. Right? So just taking procedural steps back over and over again until you can get back to this fundamental truth, and you can then sort of extrapolate that out to stuff that looks nothing like that. A lot of methods is going to be based on your ability to observe the symmetries in the situations that you're given. And so part of what I'm trying to do with these classes is show how you can break things down into simpler looking things, because you're already getting enough of the concepts from your school as far as, here's the thing, here's the question, do them. I'm trying to do something slightly different here by showing how these things can relate to simpler concepts. But okay, I mean, that's a example end to end, essentially. We worked through one where we had 1A through to D, where it basically stepped out the exact steps that we would follow in our procedure. That got us the graph. I forgot we weren't just doing the graph. We now have to move on to actually finding the maximum. So before I go on, we have done this graph now. Does anything need to be clarified further about that? Okay, let's wrap this up then. So we're trying to find the maximum. Remember that negative x's don't work because x is a length, and this one gets a bit trickier because you've now got to refer back to the actual original picture to figure out why this doesn't quite work. And it's simply because any x greater than 10 would mean that you're cutting more than 10 out of both sides of a square. And if you've only got 20 length to work with, you're not going to cut 11 from both sides. You've now run out of paper to cut out of. So the only bit we care about is this. It'll always be this hump. What we care about is getting that. How we actually get it, that's a completely different story in a tech-free world. Tech active is going to be via the fmax function. So I'll just move this over to the side. We don't need the graph anymore once we've identified that what we're looking for is a turning point. And so yeah, let's start defining. Define function 4x 10 minus x all. I made one very similar to the one we just did before. The only difference was that was squared. Nice. Okay, that's the function. Then again, fmax function, comma, x, not forgetting to put a domain in there. So if you do, you'll have something bad, right? You'll go to x equals infinity or negative infinity. That's because the actual cubic shoots off to infinities. So make sure you put your domain. So ours was from 0 to 10. That was how we had those bumps. 0 to x to 10. X is 10 on 3. Sub back into function to get the actual y value, which is the maximum. Remember, the y value is the maximum, not the x value for which there is a maximum. So in other words, what we just found was that this point up here is the point 10 on 3, comma 16,000 on 27, of which that one is the max because that is the y. All right, finish that one just on time, which is nice, or a little bit over technically. If you have any further questions, I'm happy to clarify things for the next couple of minutes. Otherwise, thanks for coming. No worries.
Thank you.
Thank you.
Thank you.
No worries. Hey Sam, you got anything for me? Or you just AFK?
No, sorry, I couldn't leave.
Oh, you couldn't leave.
Yeah, sorry.
No, you're good, mate. You're good.
Have
Is
a
it
nice
still-
night.
Yeah, you too, mate. Take care.